I'm going to talk today about a numerical method for a diffusive class of nonlocal operators. This is joint work with Cory and Loic Cappanera. Cory was a postdoc at the University of Houston, and now he's working in industry, and Loic is a colleague at the University of Houston. So our interest was in modeling evolution or non-local evolution processes described by this type of equation, where we're assuming that the convolution kernel is going to be a radially symmetric kernel that is exponentially decaying and spatially extended. So we're not assuming that the kernel is going to have a compact support. We actually allow it to be defined in the whole of the real line. In addition, we assume these further conditions on the kernel so that now this convolution operator is describing a diffusion process that is somewhere in between the standard diffusion as described by the Laplacian and anomalous diffusion as described by the fractional Laplacian. And so the motivation was because most of the, or rather I should say that these type of equations that come from problems that, for example, reaction diffusion equations that involve a fast component. And the way to derive the equation is to, for example, look at the fast component, send these epsilon parameter to 0, and then solve for the fast variable in terms of the slow variable and insert that back into the equation. So the result is going to be this non-local set of equations where now the convolution represents a non-local form of interaction. Other problems where you see this type of model comes from problems in population dynamics or including problems that come from neural field models. So this is kind of like the motivation. And the type of phenomena that I'm interested in are these patterns that emerge in some of these models. And one of the things that you notice from these patterns is that usually the length scales of the solutions is very small compared to the system size or the experimental setup. And so in general, the equations are usually posed on the whole plane or the whole real line or R3. This is particularly the case when you're studying vegetation patterns, for example, or when you look at proving the existence of solutions traveling waves or spiral waves for oscillatory media. Now, the issue is that now you want to model this, and when you try to model them, you no longer have the option of modeling this on the whole real line, so you have to come back to a finite domain. So there's an issue of how do you deal with the boundary conditions and what kind of boundary conditions you're going to use. And so what I wanted to do was come up with a method that allows you to approximate well the whole real line problem without having to assume something like boundary conditions, but also obtain a scheme that is also easy enough that you can go between the two things. So you can apply non-local Dirichlet boundary conditions or non-local Neumann boundary conditions, but that also allows you to approximate these whole real line problems. And so for now, we're just sticking to the one-dimensional case because it's the easiest case just to test these ideas. And we have we came up with a couple of schemes. So one for bounded domains where you are actually assuming that you have non-local Dirichlet boundary conditions so that you assume the value of the solution in the complement of the domain of interest. And in this particular case, we consider kernels that could take on negative values so long as they have a positive tail. It seems like the scheme converges. And we have a proof for that. In the case of non-local Neumann boundary conditions, because these boundary conditions allows you to write the problem in a way that is very similar to the unbounded domain case, then the non-local Neumann boundary problem is kind of like a subclass of the unbounded domain example. And here what you can notice is that when you're dealing with these non-local Neumann boundary conditions, what is going to happen is that the source term that you're trying to solve for is going to be split into the thing that is actually the source term and the part that is describing the flux that's coming from the outer boundary. So by the way, I didn't specify this. So even though we're interested in these time evolution problems, what I'm doing here is trying to just deal with the steady state for now, and then you can implement later a time stepping method as you wish. So that's the general idea. The other thing that I wanted to mention is that, well, how are we going to do this? What are the issues that come up? So one of the issues is that, at least in the bounded domain case, it is well known that these type of problems is well posed. But in the case of unbounded domains, it's not clear that this is necessarily the case. And so what I want to emphasize here is just the analysis that went into proving that these unbounded domain problems are well posed, and that using these analyses, you do gain information that is important and that actually allows us to create a scheme that is a good scheme. So what I want to do in the next couple of slides is go a little bit through these analysis so that it becomes clear how this analysis is helping us in creating the schemes, at least in the unbounded domain case. So why is it that when you're considering the problem in unbounded domains, why is it that the problem is now well posed? So the main idea is that that the problem comes from the type of spaces that you're using. So if you set up this convolution operator between the standard subweb spaces, what you realize is that you have a zero eigenvalue embedded in the essential spectrum. And what that means for you is that the operator itself doesn't have a closed range. And so given any source term, you're not always guaranteed that you're going to have a unique solution that corresponds to that particular source term. Perhaps this is a little bit easier to see when you consider in convolution kernels of this particular form. So here you have a convolution operator that is invertible and composed with a Laplacian. And so the idea is that the problem that you have, the reason why this operator doesn't have a closed range is because the Laplacian is not invertible from H2 to L2. And it's not invertible because it doesn't have a closed range. And it doesn't have a closed range because you're able to create these Weyl sequences. And so these sequences have a property that you can, they do not converge in H2, but they do converge once you apply the operator to it. So the image of these sequences under the operator is going to go to 0. So what you want to do is you want to try to figure out what are the correct spaces that you need to use in order to remove these Weyl sequences. And one thing that you notice is that these sequences are created with elements that are in the kernel or the null space of the operator, so in the null space of the Laplacian in this case. So for the one-dimensional case, this means getting rid of the constants and the values of x. So, and how do you do that? Well, in that case, what you want to do is you want to create or you want to consider spaces that impose some kind of algebraic growth or decay. So there's theorems that date back to the 80s that allows you to show that the Laplacian is going to be a Fredholm operator. And basically what that means is that you have a closed range and you can use some form of a Fredholm alternative in order to solve the equation. So what are these spaces? These spaces have this property that whenever you take a derivative, you are increasing the weight of the space. And so they encode, in some sense, algebraic growth into your spaces or algebraic decay. And so when you have algebraic decay, for example, what you're saying is, I don't want the kernel to have any of the constants or any of the linear terms. You are removing these Weyl sequences. You're not giving them a chance to be created. On the other hand, when you impose algebraic growth, what you're allowing is for the constants and the linear terms to be in your kernel. And so that way you are also getting rid of these Weyl sequences. And that renders your operator a Fredholm operator. Because this happens to the Laplacian, that means that this is also going to be a property that is inherited for our operators and for the type of operators that we consider. And that's mainly because these type of operators, you can decompose them into a convolution operator that is going to be something that is invertible composed with a Laplacian. And so whatever Fredholm properties you have from the Laplacian, these are going to be inherited by your operator. So what does it mean in particular? In particular, it means that you have this Fredholm alternative property. So given a source term that, say, has some kind of level of algebraic decay and that it satisfies these conditions having average equal to 0 and 0 first moment, then with these conditions and the algebraic decay, you're guaranteed that you're going to have a unique solution for this problem. And moreover, the main point here and the key idea is that if you assume that your source term is going to have a decay rate that is 1 over x to the 4th, that then you obtain that the solution that you started or that the solution that you're looking for is going to be decaying at order 1 over x squared. And so this is the information that we're going to use in constructing the scheme. So with this information, we implemented or we adapted a scheme that is based on Huang and Oberman's work. And Huang and Oberman, what they did is they created a quadrature method that they apply for the fractional Laplacian. And what we're doing here is we're just adapting their method and combining it with the ideas of, okay, how do I make my operator invertible in order to create this scheme? So the scheme is very easy. You just split your integral into 3 different portions. A portion that deals with the things that are close to the origin, a portion that is somewhere in between, and a portion that deals with the things that happen far away. So I want to talk about a little bit more about the red term that I have here, but let me explain a little bit more how we're doing the splitting. So the splitting between the middle portion and the portions that are in the far field comes from selecting these LW the correct way. So these LW is going to be chosen so that whenever you have xi minus y, that this value of x minus y, whenever you pick y values that are larger than LW, these x minus iy is going to give you points that are outside your domain of interest. So that when you're calculating this integral that appears in red, you just have to use information that lies outside the domain of interest. So this is information that you're either going to approximate or that you already know. The term in blue is something that you can calculate easily. And then the terms in black, I'll talk about them a little bit later. So let me focus again on the term on red and how you used the theory that came before. So the idea is that because the term in red uses information that is outside the domain of interest, you either know already what it is because you have the nonlocal Dirichlet boundary conditions, or you can approximate it by the decay rate of the function. So in the nonlocal Neumann problem or the realigned problem, what you're doing is you're saying, well, I don't know exactly what the u is outside in these part of the domain, but I can approximate it as a function that has the correct decay, or at least the worst case scenario for the decay. So if you know that your source term is going to decay as a 1 over x to the fourth, then you're approximating your solution as a 1x squared or 1 over x squared. And that turns out to give you enough information to get a scheme that is going to be more accurate than assuming, for example, nonlocal Dirichlet boundary conditions. And so I'll show you a little bit of the results that we have in that case. So that's basically the premise. And then to deal with the other terms, well, okay, so let me just explain a little bit more how the terms go. This is just explaining how we're writing the scheme. So the blue terms, again, this is something that you can calculate. The red terms, in the case of the Dirichlet boundary conditions, they're just going to turn into a source term, so you can move them to the other side. And then to approximate the part of the integral that is in black, then what you want to do is first approximate the singular part of the integral using the principal value. So in our cases, we usually we didn't need to approximate it using the principal value because we had kernels that were not singular at the origin. But the point is that you could probably extend this, or you can extend this to situations where your kernel is singular at the origin. And the idea is that when you do this, realize that the integrand is really an approximation for the second derivative of your unknown evaluated at that particular xi, so that then what you can do is approximate that derivative using a central difference and then just integrating your kernel against the y squared. On the other hand, for the sections of the integral that are in the middle spaces, what you want to do is you want to use a polynomial interpolation in order to approximate the integrand, and then just calculate the weights this way. Okay, so the results that we have is that we're able to prove that in the Dirichlet that this is a stable scheme that is consistent and that also converges. We also found that when you look at the inverse operator, this norm depends on the tail of the integral. So that's why we're able to use kernels that take on negative values so long as the tail of the integral is positive. You know that the scheme is stable. We prove that the scheme is H2, provided that the solution is in C4. And we also have similar results for the realigned case where we prove that the scheme is convergent. So the last thing that I want to show you is, well, okay, advertise that these results are in the paper that I have here, that the code is implemented in MATLAB, and that you can find all the examples that were in the paper. They can be found, or the code can be found here in the GitHub. And the last thing that I want to do is just show you the different results for two different types of source terms. So here, what I wanted to do is compare, okay, so if I have a problem that is posed on the whole realign, and I want to pick a scheme that is going to give me the best way to approximate that, I have options. I can approximate it using these homogeneous Neumann boundary conditions, because that's usually what you do when you have these whole realign problems and you want to truncate it and approximate them in a bounded domain. Or you can use the homogeneous Dirichlet boundary conditions. And what it turns out to be is that if your source term decays sufficiently fast, all schemes seem to be accurate. And probably what you want to do is you want to stick with the Dirichlet scheme because it's the one that is the easiest to approximate. However, when you do consider source terms that are algebraically decaying, then the scheme that actually uses the whole realign approximation and that uses the approximation of the function in the far field, that is the one that is the best scheme in this case. And so with that, I think I am good. Let me give you just another example where we tested the case where we had a kernel that was positive and negative, but that had a positive tail. We showed again that even in this case, the scheme was second order. And with that, let me thank you and acknowledge NSF support. I'll leave you with some references.